Hello, this is day 7 of chapter 12, and this is about limits. This may get a little weird. So we could look at the function 1 over x that we've seen before, and basically makes a shape something like this. All right, and it has asymptotes. These are like little imaginary lines that our graph is not coming across. So as it gets closer to it, it gets increasingly close to it forever as it goes out in either positive x direction or negative x direction, and but it never crosses it. So it's getting closer and closer and closer and closer and closer forever, but it never quite touches it. And that's our graph. So what we want to think about is like, well, what's going to happen if I start plugging in numbers? So this is some notation. It just says the limit. What's the limit as x approaches infinity if we have the function 1 over x? So as x approaches infinity, okay, so that just means like if I started plugging in, larger and larger numbers for x, what types of answers am I getting? Because then we could kind of presume that if I kept on plugging in larger numbers and I keep on getting a similar result, or a result that looks like it's indicating it's going in one specific direction, we could draw that conclusion. So if x approaches infinity of 1 over x, what's the limit? So if I plug in, 100, I get that, that's 1/100th, so 0.001. And you plug in maybe 1,000. Really, all that's doing is now you have 1/1000th, so you have 0.001. And so you keep on plugging in really large numbers. So this 1,000 is not a very large number. We're talking in like 10 trillion. We're just going to keep on adding zeros, 0.000001. And what that means is like the quantity, the overall size of this number that we get as we keep on plugging in larger numbers for x basically gets closer and closer to 0. And that's kind of also what's indicated on this graph. On the graph, as we go farther and farther out in the x direction, our graph is getting closer and closer and closer to 0, like to the height of 0 in the y direction. So we would say the limit of 1 over x as x approaches infinity is 0. Similarly, if we went to the negative x direction as x approaches negative infinity, 1 over x, the same thing's happening. We're just kind of approaching 0 still in the y direction, so we're getting closer and closer to the y-axis, or the x-axis. But we're going in the negative x direction, so we start plugging in negative numbers, really large numbers. The same thing's kind of happening. It's just approaching it from the other side of 0. We would just end up with like negative 0.000001 or whatever, which is still really close to 0. So we say that this limit, the limit is 0. Similarly, if you had x and it had some kind of an exponent there, and r is greater than 0. Now, one thing we know is that, if r is like 4, you're raising something to 4th power. It's making it, larger, more quickly. If you had something like r equals 0.5, so if your exponent was like a fraction between 0 and 1, it's basically a radical, it's a root. And so, if you had like 1,000 or whatever, and you took a square root, that's a smaller number. But again, we're talking about plugging in x values that are really large and continuing to plug in really large x values. So even if we're square rooting a really large x value, it's still a pretty big number. Then you can just plug in a bigger number. Square root it, sure, it's still going to be a pretty big number. And then you keep on, plugging in bigger and bigger numbers. Even if you're square rooting it, you're still getting a really big number. So as long as r is greater than 0, it doesn't really matter what it is. In this situation, x is just still going to 0, because we're just getting a really large number on the bottom here. It's essentially saying, 1 over something that's really big number. And 1 divided by a really big number is 0, essentially 0. The larger the number on the denominator, the smaller your overall value is. And the same thing is going to happen here with a negative number, the limit on the bottom. Except we do want to say that if you had a negative 2, let's say, and this will come up in a minute, to the fifth, this is going to be 1 over negative 32. Okay, so that's a negative number. And then if I had negative 2 to the sixth in the denominator, that's an even number, and that's going to be 64, 1 over 64. The difference between these two is that one's a positive number, one's a negative number. So that's something to just think about. So how can we say it's going to a limit of just one number? In this case, you can still see it, because 1 divided by negative 32 and 1 divided by 64, yeah, they're different signs. But they're small numbers. And if we start plugging in like a really big number for x, whether it's negative 5 million, we're going to raise it to some power, whether it's positive or negative. It's still 1 divided by a really big negative number. So it's still going to be 1 divided by something really big. It's still going to be approaching 0. It's essentially going to be so minuscule that we would think of it as 0. And then this right here, the next two examples are just saying, let's say you had a constant on top, like let's say 1,000. We have 1,000 on top, okay, and then x to the r on bottom. And if we had the same situation, we're saying as x approaches infinity, so we're not plugging in small numbers like negative 2, or in this case positive 2. We're plugging in really big numbers like 1,000,000. And even if r is just 1, so nothing really changes it, I'm still getting 1,000 over, let's say, 1,000,000, and that's not even really that big of a number. But if we see this, it's still 1 over 1,000. So even if there's a large number on top, as x approaches infinity, the numbers I'm putting on the bottom are just going to get bigger and bigger and bigger. So it's negligible. Constants on the numerator are negligible. They're inconsequential. They're not going to affect our overall limit because of the fact that we're going to infinity. We're plugging in super large numbers, and we would just keep on plugging in a bigger number after that and kind of just seeing what the fraction does. And the fraction is just going to get smaller and smaller and smaller the bigger number you put in the denominator. So 0 again, and the same thing's happening on the negative side. 0 again. All right, we have a whole bunch of formulas, and these formulas are basically just saying one thing. If you have a limit that has a whole bunch of pieces to it, like a limit of something here, and something there, we could just separate those and say, it's the same as it's the limit of this term plus the limit of this term. It's just allowing us to separate them and do all the limits individually and just see what we come up with. So all of these formulas are essentially saying the same thing. All right. There is an important trick, let's say. It's not really a trick, but it's not cheating in any way. It's making things make more sense to us rather than at first glance trying to figure it all out. So first of all, if we just think about this, we're plugging in, we want to plug in some numbers. We're going to plug in numbers that are really big. And so if I look at the top, well, the really big number is going to get multiplied by 3 and then added by 5. I mean, we're talking really big numbers. Multiplying by 3 is not going to do that much. Adding 5 is not going to do that much. And on the bottom, same thing. You have a really big number, subtract 4, which does almost nothing. So really what it looks like right now is really big number over really big number. And the top maybe a little bit bigger. I don't know. So one way we can tackle this is to divide each term like 3n, 5, n, and negative 4, by the largest power of x in the denominator. In this case, it's n, but it's fine. So the largest power of n in the denominator. So denominator right now has n minus 4. It means n is the only variable and largest power is just n. So we're dividing everything by just n. What that looks like is that, I have 3n over n. The n's would cancel. So I would just have 3. And then I have plus 5 over n. And on the bottom, n over n is just 1 minus 4 over n. And the way that this is going to help us determine what's happening is now, since we have all these separate pieces, we can just take the limit of each. So we'd say limit of, n approaches infinity of 3 plus limit of n approaching infinity of n, limit. I'm not going to write this every single time in the future because it's pretty intuitive that if we're trying to take the limit of the whole thing, it's the same as taking the limit of each of the things individually. And I just wrote that all out. It's kind of unnecessary to write it all out if you know you're taking the limit of all of them individually anyway. So here's what happens. The limit of n approaching infinity of 3, well, there's no n. So we're not, whatever we would plug in for n, there's nowhere to plug it in, we'd still just get 3. Limit of n approaching infinity of 5 over n. Well, this is a classic case where you have a constant on top that's going to not matter because we're plugging in really large numbers on the bottom. So any number on top divided by a really, really large number is going to be essentially 0. And on the bottom, limit of n approaches infinity of 1. There's no n to plug it into, so 1. Minus limit of n approaches infinity, 4 over n. Same deal. Really big number on the bottom. 4 divided by a really big number is going to be close to 0. And then you plug in an even bigger number, closer to 0. So really, this whole limit just turns into 3 over 1, or just 3. So that's why it's kind of important to use this little trick that's called that they were dividing every term in this problem by the denominator's largest power of x. So in this case, it was just n, but divided by n to each term, and then we can kind of see that everything falls away. These terms become really, the 5 and the 4 don't really matter. We're talking about really big numbers. Adding 5 or subtracting 4 doesn't matter. The only difference between the top and bottom in this problem is one of them is multiplied by 3 and the other one's multiplied by 1 or whatever. So you plug in a really big number, it's just times by 3 is what you get. So 3. Woo! Okay. So in this case, it says we're approaching negative infinity, so keep that in mind, I guess. But we would just want to do the same thing. Look at the denominator. We see the largest exponent of x is x to the 4th. So I'm going to divide everything in this fraction here by x to the 4th. We can see what happens. Okay, each term got divided by x to the 4th. Now, we can kind of almost skip a step or just kind of know where this is heading already. Anytime, we should probably be getting used to this because it's always going to happen. Anytime you have more x's on the denominator of a fraction than on the top, it's going to be 0. It's going to, as you start plugging in really big numbers, the denominator of that fraction grows larger faster than the top. So, 9 certainly isn't growing. The denominator would be growing because you're plugging in bigger and bigger numbers. So 9 over really big number, 0. 3x squared over x to the 4th, plugging in really big numbers. Well, you're squaring it on top and then multiplying by 3. Sure, that's going to make it larger. But on the denominator, you're raising to the 4th power, which is making it grow larger faster than the numerator. So essentially, just in a nutshell, anytime you have more variables on the bottom or a larger exponent of the variable on the denominator of a fraction in a limit, the denominator is going to grow faster. So whatever the top is divided by a very large number, 0. So I'm not going to rewrite this all with individual limits. I'm just going to look at it and see what's going to happen. This term is going to be 0. The 9 over x to the 4, 0. The 4 x to the 4th over x to the 4th, those will cancel out, and I'm just left with a 4. There is no, I'm not plugging in anything there. And the denominators, 8x to the 3rd over x to the 4th, the denominator has more x's, so it's going to grow faster. This is going to turn into 0. Minus 7, x to the 4th over x to the 4th, that's going to cancel out. So there's no x's, it's just a 7. And to be fair, brief explanation, this 8x to the 3rd over x to the 4th, really what happened is, and this goes for some other terms in this problem too, x to the 3rd and x to the 4th, like I have a number of these are going to cancel out. X to the 3rd and x to the 4th, leaving just one x left over on the bottom. I'd really end up with 8 over x. And so that just kind of gets rid of some of the frivolous parts of it, where now it's just a constant on top, and when you're plugging in really large numbers for x on the denominator is getting really large, and it's 0. So it's just an alternate explanation. 1 over x to the 4th, also 0. And then, for whatever reason, we just have a +1 sitting there. That's not part of this, the limit where we're plugging in terms. I mean, there's no variable there. So we would have 4 plus 0 over 0 minus 7 minus 0 to negative 7 plus 1. It means that this limit ultimately is going to go to 3/7. And all I did was just add these two fractions, 1 over 1. So you can kind of see the importance of, when you first look at this problem, it looks like a complicated nightmare. But if we're just dividing everything by the largest variable on the bottom, it has the largest exponent rather, that's on the denominator, divide everything in the problem by that, in this case x to the 4th, everything kind of just falls away. We see which things are going to converge to 0 or would have a limit of 0 for it, and then we can only focus on what's important. Okay, this is another interesting example, very necessary to get to. So on the denominator, we look to see which variable has the most amount of exponents, and it's the largest exponent. It's right here. So we need to divide everything by n to the 3rd. I do want to take I'll take a moment and explain this in a second. So if I start looking through this, I'm seeing that the some terms are going to drop off. I mean, n to the 4th over n to the 3rd. That's not going to drop off. I'm going to be left with an n after that, after I simplify this, because they're going to 3 of them are going to cancel out from top and bottom. There'd be one n left over. Somewhat similar in the opposite direction on the next one, n over n to the 3rd. I would cancel out one n from top and bottom, and I would get 1 over n squared. This is going to stay 3 over n to the 3rd, and n to the 3rd over n to the 3rd is 1. All right, so we can kind of just look at the limits. Some of these terms are going to drop off, particularly the terms that have denominators of n's where the tops aren't. So this term right here is going to turn into a 0 as we're plugging in really large numbers for n. 1 over really large number is essentially 0. 3 divided by really large number to the 3rd power, 0. And then I have a 1 here. That'll be unaffected because I'm not plugging in a number. And then we see the top has an n. So essentially, if we get rid of these, if you simplify things, we're going to get n over -1. Which then, if we're plugging in increasingly large numbers for n, all that's happening is it's being divided by -1, so it just turns negative. But increasingly large numbers, it's on the numerator. So when you plug it in, it's just a really large number. And then you divide it by -1 and make it negative. It's a really large negative number. So you get closer and closer to infinity, which isn't a real number. It's just a concept in which we're thinking of a larger and larger and larger number. What will happen is this overall quantity, n over -1, plugging in a really large number in the numerator, dividing by a negative, it's just going to turn it negative, and really large number, as you keep on plugging in really larger numbers, it's just going to keep on growing. So the limit is what you would call negative infinity, but that kind of is contradictory. It's not really a limit if it keeps on going forever. So we would say the limit, you could say it increases without bound. It's boundless. Without bound. You could say it diverges. It doesn't converge to a number. It just continues on. Increases without bound in the negative direction, you should maybe say. But ultimately, what the important thing is to know is the process in which how to get an answer here. And it just keeps on getting larger, so it's negative infinity. But in terms of practicality, what that means is it increases without bound. So there's no limit. Ugh. And we have a last example where we have a situation where we have a negative number being raised to the variable in which the limit is being raised to, or the limit is increasing. So as x approaches infinity, we got a lot of things happening here. We can still operate the same way that we have been. Let's say largest variable on the bottom, or the variable has the largest exponent on the denominator, is just an x. So divide everything by x. Okay. Well, these x's would cancel, just leaving a 1, but that's not going to do a ton. It's -2 to the x times 1 then. X over x right here on the bottom, -x divided by x is just a 1. 12 over x, we can see that that's, if I'm plugging in a really large number for x, it's going to converge to 0 or diverge. I'm sorry, converge to 0. So 0 minus 1 on the bottom, and on the top, just -2 to the x. So -2 times 1, but -2 to the x over -1 is what I ended up with. And now we can kind of just look at what might happen if we started plugging in really large numbers for x. Well, first of all, as we talked about before, even if I plug in just a number, like let's say 5, like we did before, -2 to the 5th over -1. This is going to become a -32 over -1, which is a positive 32. If I plug in the very next number, 6, the next larger number would be 6, -2 to the 6th over -1. That's 64 over -1, which is -64. So we can kind of see what's happening. Every number, sequential number that we plug in, the next one up, we get a different sign, or the opposite sign. So positive 32, -64. The next one would be positive 128. So it's really hard to say as we continue to plug in larger and larger numbers, like, 500 billion, thousand, millions, whatever, just a really large number. You're going to get some number that has a negative or a positive sign. And the next larger number after that you plug in, it's going to bounce back to the other side. It's going to say now it's positive, really large number. So in this case, because it's bouncing back and forth between positive and negative number, every increasingly large number you plug in, we can say that the limit does not exist. Does not exist. Because you're basically going to get, if you plug in an even number, you're going to get a positive or negative answer. You plug in an odd number, you're going to get a positive negative answer, the opposite one. So as we plug in increasingly large numbers, it's really indeterminate. We can't determine if it's going to positive infinity or negative infinity. because it depends on if it's an odd or even number we plug in. So in this case, we'd say the limit does not exist. So we had a couple different cases. Limit doesn't exist. For number 3 here, it increases without bound. It diverges. That's the same thing as saying limit does not exist either. I mean, it can't be a limit if it increases without bound. That's a logical contradiction and a linguistic one. And in this guy, things did work out. We were able to just use our little trick to get rid of the terms that will converge to 0, or will essentially be eliminated. And so we only look at the pieces that are important. And the pieces that are important end up being 4, -7, and then this 1 that was just hanging out there. And then the first example is probably the most pure example, in that some of the terms dropped off, became meaningless, and some of the terms held fast. And so they were the consequential ones in our problem, the 3 and the 1. All right, I hope this helped. This is kind of a hefty but brief intro of limits. All right, I hope this helps. Good luck.